We'll be talking about image snapshotters in the context of particle physics. Well, you'll see later that this actually doesn't only apply to particle physics, but also beyond, so I'm glad you're here. And before we get into the details, let's briefly introduce ourselves. I'll start with myself. So I'm a physicist, so I'm largely actually doing particle physics research at Paul Scherrer Institute, PSI, and yeah, I'm working on one of the experiments that is at CERN, then again, at the CERN Large Hadron Collider, specifically the CMS experiment. And here's Valentin.
Yeah, so hi, I'm Valentin. I'm a physicist turned software developer, and I developed a CERN VM file system that actually implements a containerd snapshotter. And we'll hear more about that later. But first, Clemens will introduce to you actually the problem that we face at CERN and why actually containerd snapshotters solve an important problem.
Great. So yeah, you heard you have two physicists right in front of you, so we'll talk a bit of physics, but not too much. So if you think about particle physics in Switzerland, well, I guess the first thing that comes to mind, a lot of water, green pasture, and so on. So there are actually two large labs in Switzerland. One is Paul Scherrer Institute, or in short, PSI. That's Switzerland's national lab for natural sciences and engineering. And then there's CERN, widely known. You've had several talks actually from CERN here at this conference, the European Laboratory for Particle Physics. And they both have in common that they have particle accelerators. So we're basically accelerating science with accelerators. And what accelerators do is, in the name, they accelerate particles. And that means, to some extent, they either shoot those accelerated particles then on targets, or they make them collide, so shoot them on each other. Right? And these experiments, or these accelerators, in principle all look very similar. So for instance, there's one that's been there at PSI since the 70s, and it's been continuously upgraded, the so-called ring cyclotron. And then there's one that you've probably heard of more often already, that's the CERN Large Hadron Collider, in short, LHC. Okay, so when these collisions or interactions happen, there needs to be some device that actually detects these particles. And one of them is the CMS experiment, and yeah, that's the one that I'm working on. It's also a pretty huge experiment, so there's a human for scale down there. So this experiment is 15 meters in height and then 25 meters in length, and we actually get a lot of collisions from the Large Hadron Collider, up to 40 million events per second, and this is happening 24/7, almost all year long. And then you can imagine that this is some kind of camera that has like 134 megapixels, but it's taking these photos, with every 25 nanoseconds. So this is a bit better than what you probably have in your pocket as your smartphone. And I mean, now what is really important is that these data are unique. So this experiment, together with the ATLAS experiment, they have been used to discover the Higgs boson. And we can actually also only measure and further investigate the Higgs boson at these experiments. So this is really unique and valuable data. Now, if we want to keep continuing analyzing these data, we actually run into the issue that, to some extent, the experiments are pretty expensive, and also the accelerator part. So we have very long-running experiments. And I think by now, at the LHC and also the CMX experiments, or the other experiments at the LHC, they're by now one of the most long-running experiments there are in the world. And you can actually see here on this timeline that the initial collisions or operations started around 2009, right? So we're now like 16 years later already. And then if you look at the end of this arrow, so this is not entirely to scale here, but the current plan is to continue taking data and colliding particles until 2041. So that's another 16 years to go. Okay, and now as software engineer, you think about, okay, now what is actually my Linux distribution or release that I can use? And you can see that, well, we initially started actually with Red Hat Enterprise Linux 5 and all derivatives of that, right? So binary compatible ones typically. So then at some point, pretty soonish, we switched to version 6. Then we have 7 running still in quite a few places, but now the majority of systems have moved to Red Hat Enterprise Linux 9, and well, somebody who can predict the future can tell me which Linux release we're going to be running in 2040. But you can tell that I mean, it's actually really important containerize all your workloads, and that's like the only way in which we can keep doing these things, because nobody wants to have like SLC, like Scientific Linux 5 or Red Hat Enterprise Linux 5 machine somewhere connected to the internet, right? So that's particularly what admins don't like. I don't know quite why, but you know, people don't do this anymore. Okay, so now on to Valentin.
Right. So I hope this doesn't come as a shock to you, but when you run a container, on average, you use about 15% of the actual data that you download from the registry. So 85% of what you download is effectively unused. Of course, you can minimize very aggressively containers for your use case, and then you're more efficient, but that's not really possible in all use cases. In particular, for particle physicists, we have huge software frameworks that do lots of things, and you might want to really package a whole experiment software into one containers in order that it's a useful standard container. So in order to execute containerized workloads efficiently is really important then to also be more efficient in actually the data that we use. And one of the most promising avenues here is the use of lazy pooling, basically the snapshotters that implement lazy pooling. The basic idea here is that a container is composed of layers. It's basically a set of tarballs and a manifest list. And what lazy pooling allows you to do is to expose all of the layers to container D without having to download all of them. Typically, this then uses some kind of internal index. That's, for example, how StarGC, one very influential lazy pooling snapshotter, works. But in the end, that means that it can start a container almost immediately, but then be slower during execution, as that's actually then where you on demand download the data that is accessed. All right. And then Clemens will talk you a bit more about the different actual implementations of lazy pooling snapshotters that exist today.
Hi, thanks, Valentin. Yeah, so there are different options around on the market, and actually I talked to some of the container D maintainers early on, and they have their session actually in parallel to ours. And I mean, this list is not complete, but this is a list of those that are basically around, and they will actually be talking about one that they will add with the next container D minor release. So they all work as plugins to container D, so I already mentioned it, and we investigated the three that are listed here in red, so the StarGZ snapshotter, the Sochi snapshotter, and then also the CERN VM FS snapshotter, and I'll go through all these in some more detail in the following. Then as a comparison, we always benchmarked everything against the traditional overlay FS snapshotter, so that doesn't do any lazy pooling. I just want to mention that there's also the Nidus snapshotter, which is also a very interesting project, but we haven't used it for our benchmarks. In principle, you'll see that I'm already giving it away now, that the performance is very similar as long as you're just using a lazy pooling snapshotter. And now some people might ask, so what if I run on like public cloud offerings? So it's a bit difficult to get like insight into this, but we found, for instance, that on Google Kubernetes Engine, there's also an image streaming service, and then on Microsoft Azure, for instance, they also have something that helps you with the image distribution. And there's also nothing that would prevent you from installing either of these snapshotters into those public cloud offerings if you wanted to do that. Okay. Now, also, the good thing is there's actually no risk in using lazy snapshotters, because all of them are implemented in a way that they will actually fall back to what I call here now legacy pooling. So I'll just go back to downloading the entire image, unpacking it, and then executing it in case the image isn't available in a way that you can perform lazy pooling. Okay. So now, this lazy pooling mechanism, or the way that enables lazy pooling, is implemented in different ways, and that's basically how you can differentiate between the different snapshotters. So the first one that I'll discuss here is the so-called StarGZ snapshotter, and the idea is basically in the name is to use images in a searchable StarGZ format. So that actually then required that the images that you push into your registry are different. So they actually use an extension to the gzip format, so that you can search these images. In the standard OCI formats, you basically have to take the entire layer blob and extract it to get a single file entry. Now, by basically packaging everything into smaller tarballs, you can extract specific files individually, and that then enables this lazy pulling. Also, here on the top right, you'll always see there's a QR code, and also the title of the slide, if you want to download them, is actually then links to the repositories or the documentation. Okay. So now, one thing that can actually happen if you're doing lazy pulling, if you're picking all the bits and pieces from your image or from your individual layers, you can actually see that things somehow slow down. Valentin already mentioned this. So there's one way, for instance, that in the StarGZ snapshotter, you can improve this by, for instance, using a mechanism that's prioritizing the files. Okay, and I've been talking too long on this slide. So that, sorry, let me just go back. That will give you the option to then have a bunch of files prioritized for download, and you don't see these delays later on. Okay. Now, the big caveat that we've seen also when trying to convince other people to actually use this is that you actually have to rebuild the images in these in this extended StarGZ format. Right. So basically, you have to recreate or convert all your images, and that's something that makes adoption a bit difficult or makes it somewhat slow. So the Sochi snapshotter, or seekable OCI snapshotter, is actually then a fork of the StarGZ snapshotter, which somehow addresses this problem by adding a separate index artifact to the image that is then hosted in parallel in the registry. So that has the big advantage that you do not require a build time conversion step, and you can actually add this index artifact after the fact, right? So you basically just have a job that, or a command that analyzes the image and then adds the information about on where you actually have the files that you need to extract from each layer as some kind of index artifact or manifest in parallel then in the registry. Okay, and then for optimization, you can, for instance, then also configure a minimum layer size for index. If a layer is particularly small, it doesn't necessarily make sense to also index that, but you might just download the entire thing and unzip it. And the default here is something like 10 megabytes, and something reasonable. So now they actually made then the deliberate choice of not prioritizing, not having this file prioritization, which again, comes with an advantage because you can then also share layers with other images. Right, so in principle, you can, if you already have always the same base image and only something light on top, you can share this because you're not moving around things in your images, and you're just always using the same base. Okay. Now, there's also a small caveat to this, which is that not all registries support additional artifacts. So we're actually using quite a lot of GitLab, and the GitLab registry does not support these additional artifacts, but for instance, Harbor does that without any issue. So you just have to be aware of this, and this is also then listed in the documentation here. Okay, and last but not least, before I hand then over to Valentin to give you more details, there's the CVMFS snapshotter. And the idea is to use so-called unpacked images on CVMFS. And I just want to mention here that this is somewhat similar to the NIDA snapshotter, and you there then rely on some additional content distribution service that then by definition here is not OCI compatible. But yeah, I'll hand over to the CVMFS expert now. To give you more details on that.
So now I'd like to give you a bit more background on what is CVMFS and how we built our own containerd snapshotter. So CVMFS is a global read-only file system for software distribution. And at its core, it's really an on-demand streaming service for scientific software. think like Spotify, but you can download basically all types of scientific software. So what happens is that you have on your computer this global directory /CVMFS, and whenever you access or open files on this directory, actually what happens behind the scenes is that they get downloaded and cached from a remote server that offers them. Basically, someone publishes the catalog of available software, and then it's on demand available to you. So this is implemented as a file system in user space so that it's easily usable on all worker nodes in a distributed computing environment like we have at CERN, and it's really heavily optimized for storing and distributing software. So what we can do is we have an object store that backs the CVMFS that allows to deduplicate files and even chunks like at the sub-file level. We have many levels of caching to use basically plain HTTP transport, and then we have verification of data integrity, and we can compress data. To give you a few numbers, so CVMFS is quite a mature project by now. It's more than 15 years old. We have around 4 billion files in the /CVMFS tree. These come from a variety of scientific experiments. There's the big LHC experiments, but then there's also experiments from astronomy, LSST, then the Euclid experiment from the European Space Agency, and a long tail of smaller experiments that make use of CVMFS as well to deploy their software to distributed computing resources all around the world. So here you find as well a picture from the worldwide LHC computing grid that heavily uses CVMFS to distribute software. And actually the biggest repository that we have is unpacked.cern.ch, which stores container images unpacked. And I'm going to talk a bit about this later. Just wanted to highlight first that apart from the many academic users that we also have a very nice collaboration with Jump Trading, a financial trading company, which has a very interesting use case for CVMFS. They use it as a file system view on their market data archive. So while it's optimized for software, it's also possible to use as a file system view on external data. We also want to thank them for supporting the open source and our development of CVMFS. And then there is as well EASY. EASY is a project of European sysadmins that tries to build a common software stack of HPC applications, and those are as well then deployed on CVMFS. And then the idea would be that any HPC in Europe that is participating can access the same software stack of HPC packages. So how do we use containers with CVMFS? So we provide basically tooling to take the whole container image and unpack it in a CVMFS registry. This allows us to use the backing object store, deduplicate any files that can be deduplicated, and then basically access the whole container directly in a registry. So it's like this. This, of course, requires a bit of infrastructure for the servers and the workflows to unpack images, but once you have them there, it's in the end like a very efficient way to access images. And I'd like to show this with a short recorded demo. The nice thing about these snapshotters is that they're very transparent. So basically the user doesn't really see what's happening behind the scenes. But here we want to actually get a few more technical details, and for this I've written like a small application that shows a few additional pieces of information. So down here you have a widget that shows the network and the bytes downloaded. And on the right here, there's two widgets that basically, through the Linux iNotify interface, basically just show the activity in two folders. One is the basic overlay.fs snapshot folder from containerd, and then there is the CVMFS cache. And now let's see what happens when we actually run CVMFS. So first I'm going to pull a standard image from the normal container ID registry, and we see basically that we're downloading around 400 megabytes, and this then all gets put into the snapshotter directory. So you're no doubt familiar with all of this, and you can see that as you finish basically the pulling of the image, you have all of the files then basically available directly. Now, what's going to happen next is that I'm going to remove the image So there is no longer on the local host, and then use the CVMFS snapshotter. And you see that the behavior here will be very, very different. So we use basically again pull, and then just have to provide the snapshotter argument. So we use the CVMFS snapshotter. And then basically pull the same image. And here, basically, as was mentioned before, this is basically instantaneous. So it only needs to fetch the manifest and then verify that all of the layers are available on CVMFS. Then actually, once you access anything on, once you run this image, then of course we can't quite do magic. So at one point we actually do need to do the download and start things. So if I actually then do something inside this container here, sort of as importing something that's non-trivial, then everything gets actually downloaded and accessed. Of course, there's a certain latency when you do an interactive use. But this is usually way more efficient. You can also see that actually what you get in the files are really files the chunks of the files that are accessed. So that's kind of like lets you be very efficient here. All right. So far for the demo, and now Clemens will actually give up. Like this was a very intuitive presentation of this, but we also actually did a bit more rigorous benchmarking, which Clemens is now going to present.
Okay, thanks. Yeah, so we're actually going to look at the same image. So now we just arbitrarily chose a Python 3.9 image from like a Docker hub. And here on the left-hand side, you can actually now see comparing the different snapshotters, the data downloaded in megabytes. Okay, and you can see that the overlay FS, downloads the entire compressed image, whereas all the snapshotters they download significantly less. So something like 10% or even less of the data. And you can see that there's some differences here that has to do with the way that the snapshotters work, and also how they're configured. But I mean, you can see that there's a significant reduction. So if you have to pay for downloading things from a registry, this is something that you might consider to use. Also, then if you look at the right-hand side, you see the time in seconds, again, comparing the different snapshotters. And you can see that before something happens. So all we did is basically we have a workload that is like something like a nerdctl run, and then something like Python print hello. Okay, so really doing something very trivial, but you can see that of course the overlay somehow limited by the network throughput, right? Because it needs to download everything. So here it took us something like 15 seconds to run, and then in light green you can see the time until we're actually ready to execute our workload. Okay, and you can see that again the other, so the lazy pulling snapshotters, they are very comparable. I mean, they take a bit more time to actually then run the workload, but you're almost instantaneously in the terminal or the REPL, and can get things started. Okay, so now we did this for something slightly more complicated. So there's a software that is used widely in the CERN community that is called root. It has nothing to do with privileged access. It's something that we use really for data analysis, and that's here using a specific version based on Ubuntu Linux distribution. Now here comparing again first the data throughput, and now we're doing this for different complexities, right? So the first thing is just like getting the bash print in place, so that's shown in red. Then starting Python, so that's doing a bit more than just getting our shell ready. And then we do some importing of here root, because we download a root image, so there's the Python bindings to this root software available, and you can see that at that point, you actually start downloading significant amounts of data. And then we're doing something like filling a histogram in a random way using this Python root implementation. And again, you can see, I'm somehow repeating myself, you can see comparable performance across the lazy pulling snapshotters, and you can actually see that this is a somewhat already optimized image, because now we're actually using more than 20% of the image already, right? And in other cases, you might actually not have, let's say, optimized images in there, and also then maybe for the data scientists, you can actually see that import statements can be quite expensive, because all of a sudden you start downloading like 20% of the overall image. And last but not least, now looking at time again, you can see, okay, there's some fluctuations here in our overall timing, but you can see that, of course, then this downloading adds time to our overall execution. So, I mean, the overall execution is a matter of maybe 1 or 2 seconds. It's not really taking a lot of time. You can see that here on the left-hand side for the overlay FS, right? So the execution is something like 2 or 3 seconds, and so the delays then in an execution for the lazy pulling snapshotters is really because you execute a command and then the things are downloaded from the registry or from your content distribution system. So you lose some time because of that, right? But I mean, you've started much sooner. So if you have now very, very long-running workloads, it probably doesn't matter anymore. For short-running workloads, you'll still probably have an advantage using lazy pulling. Okay. So that already brings me to the summary. So, I mean, first thing to note is it's really great that Containerd has this plugin system, because it basically allows anybody to write these snapshotters. Now here we looked specifically at the lazy pulling snapshotters, and they basically have 2 major advantages. You can almost instantaneously start your workloads, and also you significantly reduce the amount of data downloaded, and you don't have to tell your users. You really try to optimize how you build your images, because it doesn't really matter anymore at that point. Okay. Now we've shown you a couple of different options. Which one you use depends a bit on your personal use case and also the cluster setup. But I think the bottom line or message here is, don't be lazy. Use the lazy pulling snapshotter, because we haven't found any disadvantages to using them, and basically only advantages. And if you have any feedback for us, there's the link that leads you to scat.com with the feedback button. So yeah, thank you, and we're also happy to take any questions. Yeah, so there's the microphone. If you have any questions, there's one. Yeah.
So you benchmarked it against popular binaries that are used at CERN, yeah? Executables. However, have you tried having an image with a lot of small files or few large files, and then benchmarking it against those 2 use cases?
Yeah, so we have actually tried that. So if you have a lot of small files, you can actually see that this gets a bit problematic, so things slow down, right? So then, I mean, there are like these ways of optimizing things. For instance, if you're using the Sochi snapshotter, just don't bother about like figuring out where these small files are, but just download an entire layer of those small files. Yeah, but we've seen that in this case, it's actually a very good point that you mentioned it, this is like not the lazy pulling snapshotters don't look that good anymore. Okay, but I think we also created very artificially small files, and then like 100,000 of them, and then we could see that things really slow down. But so it's a very good question. Thank you.
And in case of big files, can your solution also download chunks of big files, depending on random read?
Yeah, for the CVMFS snapshot, that internally chunks files in a configurable size, and that definitely does help with all kinds of network problems.
Thank you.